So problem set 2 was just due here at 1 o'clock. The questions, the questions on these problem sets, some of them originated with me, some of them were created by people entirely separate from me, but a lot of them originated as open-ended questions and have been converted to multiple choice questions. Long and short of it is, writing good multiple choice questions is surprisingly difficult. It's one of the most challenging things I end up doing, period. And for the exams, I write them all myself. Consequences of letting other people do it is some of them have answers that I kind of think are iffy, occasionally just plain wrong, and I will try not to assign, to minimize your exposure to questions that are ambiguous or just don't have the right answer, really. Lots of ways questions can go wrong. So I'm sorry that I can't write them all myself. I can't use the website and write them. I can't write ones for the website directly. Too much bureaucracy between me and having them come up. So back to physics things. There are things that sort of left behind in topics that I want to bring back because they're just useful. And many of the questions on the problem set dealt with levers. And in fact, I want to go back to levers because they're part of your lives. You use them every time. Every time you open your notebook, laptop, whatever, you're making something pivot around a hinge. And if you grab the laptop like this, say, and open it, it's relatively easy because you have a long lever arm between the hinge and where you're grabbing it. But if you try to open or close your laptop by grabbing it very close to the hinges, it doesn't work. So you live with this all the time. So I just want to make sure that you're clear on a couple of the tools. In fact, the tools that I talked about that showed up in the problem sets. To generalize levers completely is a little difficult, but let me say, there are approximately, most levers that you encounter, and most levers you encounter involve a pivot about which the rotation is going to occur, and two opposing influences. For example, you trying to rotate the lever one way, and something else trying to rotate the lever the other way. And it's a battle between you, and the battle involves torques. But you often will produce those torques using forces. And so the seesaw is a pretty nice general example of a lever. If you want to lift, let's lift little guy here. If I want to lift little guy's weight is tending to rotate this lever according to the right-hand rule convention toward you. And it's a nice shorthand way of saying how the rotation is going to occur. To say that from over in this perspective it's going to rotate counterclockwise is a much wordier way. So the right-hand rule and those conventions give you a way of saying it in just one word often. So we want to have it rotate toward you. If I push down on this lever, on this side of the lever, with a force downward, that creates a torque where there's the lever arm, there's the force, and my thumb is pointing away from you. That's a torque away from us according to this convention. So my torque and the weight's torque are in opposite directions. Okay with that? And at this point, they're both present, but they're equal and opposite. The weight has got some help from the table to really just exactly balance my torque. But if I apply a really big torque, of course, I can cause angular acceleration in this thing, and it begins to rotate. So this is just an example of a lever. It's not a terribly interesting one, because I have to push, the weight of that guy is about 10 newtons. I have to push down with a force of 10 newtons to lift the weight 10 newtons. It's sort of boring. But suppose I want to lift this guy. Now, okay, that guy weighs 50 newtons, which is more than 10 pounds. Now I have to push down. This is no fun, okay? So what do? Shrink that guy's lever arm. Bring the pivot in. I run the risk of having this fall off, but now I can do it with a much smaller force. So I am I have leverage or mechanical advantage, which are somewhat vague terms, but the idea is that with a modest force pushing downward here at that big lever arm, I can cause the lever to push up on the heavy guy with a big force, because the big guy doesn't have much of a lever arm. So the full story here involves the torques. I'm producing a torque on this beam. Big guy is producing a torque on this beam. They are presently equal and opposite. How do I know? No angular acceleration. But I'm producing my torque with a small force exerted at a large lever arm, and big guy is producing big guy's torque with a big force and a small lever arm. Any issues or questions about this so far? Yeah. Is it a matter of big guy having a small lever arm or me having a large one? It's the ratio of the two. So right now the ratio is totally in my favor. My lever arm is a factor of 4, say, bigger than big guys. And that's where the lever arm issue matters. It's always ratios. Is that okay with everybody? I'm able to lift big guy this way, and this kind of a lever has people bin them into classes. This is like class 1 or something. Who cares? The name doesn't matter. This is a different kind of lever, just as useful though. This is sort of the wheelbarrow lever. Now, if I want to lift big guy, if big guy's here, I have to lift big guy's entire weight, okay, right? If I put big guy there, now big guy is again exerting a torque on this bar in the opposite direction from me, because now I'm lifting. So my torque is lever arm up, it's toward you. And big guy's torque, it's lever arm down, it's away from you. So again, we're exerting equal and opposite torques about the pivot. But again, I can produce that torque with a small force exerted far from the pivot, and big guy produces torque with a big force exerted close to the pivot. Okay, so this is another lever. And in all of these, as a second observation about this, in all of these levers, energy is conserved because it's a conserved quantity. The work that I do, for example, in lifting this lever and consequently lifting big guy is primarily going into big guy's gravitational potential energy. I'm lifting him off him or her off the table. You'll notice that I am exerting a small force in raising big guy. Small force over a long distance, because I got to move the lever a long distance compared to how much the big guy rises. Big guy is traveling upward. It's being pushed on hard by the lever, enough to support big guy's weight. But big guy isn't moving very far. So long and short of it is, I'm doing work with a small force exerted over a long distance, and it's going into big guy by way of a big force exerted over a small distance. The product of force times distance is the same. My energy goes completely into big guy, apart from whatever goes into the bar. All right, so that is a general observation about levers. Levers often allow you to do the work that you want to do, such as lifting this big heavy thing in a wheelbarrow. But it allows you to exchange force for distance or distance for force. You can do the same work using a smaller force over a longer distance, or sometimes you actually want a bigger force over a shorter distance. For example, if you want to fling something, and let me give you an example of this initially. You want to fling something like little guy, okay? So now you want to get little guy really moving. You put big guy on here. Oh, it wasn't, that worked, but it wasn't as dramatic as I might have liked. Big guy is using a big force exerted over a small distance to cause little guy to move a long distance, albeit lifting it with a small force. So we've done the reverse trade. And when you fling something with a stick, we don't have a lacrosse stick, but that would be a better choice. But I'm going to use big forces in here to create my torque. The ball which is out at a much farther lever arm, the forces involved will be small, but the point of a lever like this is I can get I can get the ball moving very fast. I can chase it with the plastic, exerting a forward force on it. It's a small force because it's way out. It's out at a long lever arm, so the torque. I'm producing a torque. The ball is producing a torque in the opposite direction, even as I do that. Those two torques are fighting each other. My torque actually is larger than the ball's torque, and as a result, the whole thing undergoes angular acceleration. And the ball gets flicked off as the thing whips around. It gets very wordy and logically complicated, and I try to keep it simple. But you can imagine, two torques, the ball doesn't want to go. It's got inertia. My hand says, yes, you're going to go. I'm going to twist. So I twist, the ball resists. We're both exerting torques on the flinger in opposite directions. My torque is stronger than the ball's torque. The thing undergoes angular acceleration. Okay? The ball's torque comes about because it exerts a small force on the flinger, technical term, flinger. Small force, but it's at a large lever arm. So there's only a small force between these two things. It's a styrofoam or something, foam. And that small force is enough to make this little guy accelerate dramatically. Translational motion. Force causes acceleration. So it accelerates up to very high speed, and off it goes, right? Incidentally, this toy is, okay, what it really is good for, and this has come up before, like, what does spin do? Let me put spin on this ball. Do you see how it's going straight or even rising? It's a curveball thrower. The air matters, and we'll come back to the air later on. Okay. Another example of levers before I leave levers. I talked about a crowbar. I talked about, the questions talked about a crowbar. The questions talked about openers. It would be nice to give you a photograph, some image to know what we're talking about. But you should know how a crowbar works and everything related to crowbars. A crowbar, suppose you want to lift. Sorry. Suppose you want to lift big guy here. And instead of being a 5 kilogram mass, suppose it was a 500 kilogram mass. There's no way I could get it off the table myself. But if I can get the crowbar under it, which I've just done, the pivot that forms with the table is right about here. So big guy now is pushing down on the crowbar that far from the pivot. It has almost no lever arm. Consequently, it's having a terrible time producing any decent torque, even though it pushes hard. I'm way out here at a big lever arm, so even with a modest force, I can produce a lot of torque on the bar. So my torque can overwhelm big guy's torque, and up he goes. So all these tools, this is for lifting or prying something apart. You want to tear two things apart that you couldn't possibly do it with your hands. You put the crowbar in there, twist it, and it summons these gigantic forces because they're exerted very close to the pivot. As before, the energy, it's always true, the energy you do, the work you do moving the crowbar involves a small force over a long distance, and it shows up in the action that the crowbar is causing as a huge force over a short distance. Energy, your work goes into the other object with a different balance between force and distance. All right? Any more levery things? Okay, so that was one thing I want to go back to, make sure you're all aware of levers. And I could do now I won't do the fun and games over, think of all levers, but recognize levers when you encounter them. We already saw about ramps, incidentally. Ramps also provide mechanical advantage. You can lift the grocery cart, the very, very heavy grocery cart, you can lift it upward, pack it full of gravitational potential energy, and you could do it with small forces. The consequence, though, is you have to do it over long distances. You have traded force for distance. Yeah, the force is smaller, but the distance is greater, and that's a type of mechanical advantage. And in short, nearly all the simple machines you learned about somewhere in K through 12, finally, what's under the hood? What are they actually doing? They're giving you this mechanical advantage this way. They're allowing you to do the work you want to do frequently with a different arrangement of force and distance, or equivalent to force and distance. Okay? And hopefully you'll remember that somewhere down the road and it'll be useful to you. Having said force and distance, I also want to point out, I'll just not pursue it more than just pointing it out, is I've told you that you can do work, the recipe for doing mechanical work, and therefore conveying energy mechanically. The recipe is simple. You exert a force on the object, and the object has to move a distance in the direction of your force, right? That's the translational form of work. There is a rotational form, and it shows up in enough in your life too that you might as well recognize it when it occurs. You can do rotational work on an object by exerting a torque on it and having it rotate a distance in the direction of your torque. And the distance is not the right word, an angle in the direction of your work. So it's torque times angle. And the angle, the unit in which to measure the angle, for better or worse, is the radian, not degrees. Degrees is a completely human-created, artificial measure of angle, unit of angle. Radian's natural. Mathematics loves the radian. So you can do work by twisting something and having it turn in the direction of your torque. And this shows up, oh gosh, in the wheels of your car, or your bicycle, or in a drill as it turns around and around and struggles to go into it needs to be twisted to go into a piece of wood. In the propeller on a plane. It's again mechanical work, but it's done with torques and angles. All right? So I've said it. All right. Another thing to come back to before I get back to wheels is this question, and I'll actually ask it to you. Do your clickery thing. Here's a question coming to you. How do I do this? Let's see. Hi. Yeah, how far off into the distance can we see each other? I can get this. I can get this. Yay! All right. I'm satisfied with very simple successes. All right. So if you and a child, half your height, lean out over a pool. So you grab onto something, the two of you, and you're both leaning over the pool. And here's you, here's the kid. The two of you lean out over the pool, and you're going to pivot in about your feet. So your feet are down here. So this is the pivot. You lean out, and you let go simultaneously. Who goes flat and enters the pool first? You okay with the question, or questions about the question? Who hits first? You or short stuff? All right, see what you think. It's not a trivial question. It is a hard question, actually. So if you get it wrong, that's fine. I'll give you 30 seconds, and then call it. Or maybe 40 seconds. Okay, 3, 2, 1, and the majority are going for small child, but a substantial number of you are going for you. It is the small child, and that is, as I say, it's not a trivial observation. And I could spend forever trying to justify all the going through the careful explanation. Let me give you the basic idea here. When something tips over by its base, so we'll just let the kids are resilient, they can fall a couple times, we're okay. Okay, so when this kid falls, they are undergoing angular acceleration about their feet, right? So that involved angular acceleration. So there was a torque that caused that angular acceleration, and there was a rotational mass that resisted it. So this is Newton's second law of rotational motion. The torque is the cause, the rotational mass is the resistance, and the ratio of the two is the angular acceleration. So in fact, the question is, who undergoes the faster angular acceleration? Well, where's the torque come from? The torque is a gravitational torque. It's caused by gravity. If we got rid of gravity, the kid could just hang out there at the cockeyed angle and it would be fine. So gravity's doing the job. And gravity effectively acts at the center of gravity of the kid, which is right around here, halfway up, halfway down. That's the effective location of the kid's weight. So the kid's weight is out here. It's pulling down, not quite at right angles to the kid, but close enough, let's say. So there's a downward force here at a lever arm like that. So the lever arm, this is a 1 meter stick. So that's half a meter. So it's a weight of the kid at half a meter. That produces the torque that causes the kid to fall. Okay? How about the rotational mass? The rotational mass of the kid, about the kid's foot. You got to consider where the pivot is to figure out the rotational mass. When you rotate the kid about the kid's foot, every portion of mass, of actual ordinary mass, contributes, and they contribute in proportion to the square of how far they are away from the pivot. So these portions in here don't count for much. This one does a lot. It's considerably farther away, and therefore you square that distance, multiply by the amount of mass there, and you get it. So that's the origin of the rotational mass. So it's the gravitational torque divided by the rotational mass that governs how fast he goes over. So let's shift over to you. Here's you. How does the torque, the gravitational torque on you compare? Well, first off, we'll assume that you're uniform people. You know, the physicists just assume simplicity, right? Okay, so you weigh twice as much as the kid because you're twice as tall, of course. All right. So twice the weight, but it also, the center of gravity is twice as far from the pivot because you're twice as tall. So the torque that gravity exerts on you is 2 times 2 equals 4. It's 4 times the kid's torque. Twice the weight and twice the lever arm. Is that okay? So for you, the torque is 4 times as much as for the kid. And that by itself would mean you'd hit the water way faster. However, what about your rotational mass? Well, your rotational mass, again, is composed of every individual piece of mass times the square of its distance. Well, the distances involved here are bigger, and a lot bigger. You've got twice the mass, and the effective, so the average location of that mass is here, twice as far away from the pivot as for the kid. So there's twice the mass, and on average, it's twice as far from the pivot. But you got to work with that twice as far squared, because mass contributes according to the square of its distance from the pivot in creating rotational mass. Long and short of that is that your rotational mass is not a factor of 4 greater than the kid. It's a factor of 8. Questions about the factor of 8? It involves that square of distance. So you experience 4 times the torque, but you have 8 times the resistance to angular acceleration. You got 8 times the rotational mass. You're fighting the rotation like crazy. This incidentally, if you compare these two, you know the fun and games that I did with Alex the other day with the 2 sticks, you can do it with just ordinary sticks. This one's easy to make it undergo angular acceleration. I can shake it rotationally, no problem. It's got a small rotational mass. This guy, I'll go as fast as I can. You know, this is about it, because it's got 8 times the rotational mass of this guy. So the consequence of all that is, who hits the water first? The kid. So short things tip over more easily. So tools for living. Be careful about tall things tipping over. They struggle to do it. They've got gigantic rotational masses. that slow the fall a lot. And they, inanimate objects that they are, they sometimes figure out that they can get to the ground faster by braking during the fall. If the tree that you're cutting over, you're cutting is tipping over, the old rotten, nasty tree that you're toppling, if it broke in half or broke here somewhere at the base, the bottom would become short and would tip over fast. And the top would simply fall, no longer having a pivot. It's just on its own. And that happens. So there are historic photographs of giant, I don't know about trees, but certainly giant chimneys, like factory chimneys, a couple hundred feet tall. When they topple those, they start to topple and then they break. And the broken top just drops. Otherwise, they would tip over like, da-da. You know, it would be a week before they came down. So they break. Where the problem occurs in your lives, be careful cutting trees, particularly trees that can't, that are fragile, that have, you know, they're old weathered junk. They often will break during the fall in order to because of that giant rotational mass problem, and the top part drops straight down, and people get clobbered or killed, worse, by falling tops of trees as the thing snaps trying to reduce its rotational mass. All right? All right, I think I've done everything I wanted to say about sort of the world. You know, this all goes back to seesaws and seesaws friends, all the levers. Okay, back to wheels, and wheels, the purpose of wheels, or a purpose of wheels, is to introduce yet another force. We've got support forces, gravity, that may be it. So another new force to bring in is the world of frictional forces. And frictional forces, I told you the support forces are perpendicular to surfaces. Frictional forces are parallel to surfaces along them. And a force that's cockeyed, a force that's in this direction, say. This is support, this is friction, and something that's in between is a mixture of support and friction. It's nothing new. Frictional forces act to reduce the relative velocity between two surfaces. So I did this last time, but let me just flesh the rest out. These two surfaces, wagon and table, push on each other horizontally, that is parallel to their surfaces, with frictional forces. If no sliding is occurring, the frictional force has the name static friction. And microscopically, static friction, I mean, the way I like to envision it is imagine zooming in on the two surfaces until they look like the bristles of hairbrushes. They're not perfectly flat. No, it's not possible to make a surface that is completely flat down to every possible microscopic level. They have structure. And if you think of that surface as just the bristles of a hairbrush and the bristles of another hairbrush, the two hairbrushes interdigitate to some extent. Their bristles are woven into each other. And to get them started sliding, one hairbrush across the other, you got the bristles pushing against each other. They don't want to start. That's static friction. And static friction basically will adjust to prevent any relative motion up to a limit. If you exert no leftward force on the wagon, if I exert no leftward force on the wagon, the table's frictional force on the wagon is 0.2. It's happy. If I exert 1 Newton to the left, it pushes 1 Newton to the left. I could get those scales out and show you this, but it's going to, actually I will, for some reasons. There is a limit to static friction. Here, I'm pulling with 2 newtons to the left, and the friction is balancing me perfectly. 4 newtons, 6 newtons, 8 newtons, 10. Somewhere around here, sliding will begin. We're at 12 newtons of static friction, up, and now it's slipped. And the funny thing is, look what's left, a much smaller value. So what I hope you had a chance to see was static friction adjusted itself. The static frictional force that the table exerted on the wagon was variable. It just always matched me, up to 14 newtons, at which point I said, can't do any better. I can't push harder. It's as though the bristles finally started to move across each other, through each other, and they're hitting and colliding incidentally as they move. And once that happens, it's not static friction anymore. The surfaces now are sliding across one another. And the friction changes character. It now is called sliding friction, or you may know it as dynamic friction. And it's a single value. It's not adjustable anymore. Let me try to get it back, that same effect. 2 newtons of static, 4, 6, 8 newtons of static, 10, up, and now it's sliding. And it's smaller than 10. So a takeaway from this is that static friction is adjustable up to a maximum, and once sliding friction appears, once the sliding starts, it exerts approximately a steady force trying to stop the sliding, but that steady force is typically smaller than the peak of static friction. So prior to skidding, sliding friction is basically skidding, and other names for it. Before something starts to skid, it pushes variably up to a limit, and once it starts to skid, it pushes consistently, typically at a smaller value. So I think I've got it. This is a question. Yeah. So here comes this question. And I did do it. Oh, come on. Hey! Technology. All right. Yeah, teach it, but don't use it. Burning rubber. Suppose you're trying to make your car accelerate. Perhaps you're at a red light, suddenly turns green. You feel like impressing everybody around you by how fast your Tesla in ludicrous mode will pick up speed. So the question is, do you want to skid the wheels, the tires, or do you want to go just short of skidding the tires? So the tires grip but don't actually slide on the pavement. You okay with the difference? You may not have thought of the skidding process as fundamentally different kind of friction from the not, but it is the case. Any questions about the question? See what you think. The answer is probably pretty obvious. Yeah. Once in a while, you get this. Oh, I'm now up to 2 people on the other side. Oh, yeah, D is definitely a good answer here. Yo, he is winning. It's a horse race. I don't do politics, but you can imagine I could have, 11 choices? All right. Okay, so I'll stop. We're having fun. You don't want to skid. Skidding, if you skid the tires of your car, the bottom portion of rubber is actively moving relative to the pavement. It is dynamics or sliding friction that you're experiencing. And that's typically not as strong a horizontal force as you can get if the 2 surfaces actually grip each other and don't move relative to one another, which is static friction. Yeah, there's a lot of movement in a car relative to some things, but if you go down to the pavement and you look at the tire on the pavement, even when the car is traveling 100 miles an hour, the pavement's motionless, obviously, and the tire's bottom surface is also motionless. Okay? The tire's surface actually slows to a dead stop even when you're driving to Richmond at 60 miles an hour, or 80. Or you're ignoring those signs that say speed enforced by aircraft and driving 100. All right? The tire actually stops dead right there on the surface. And instantly, just to make you realize it, the top surface of the tire is going towards Richmond twice as fast as the car. It's a remarkable, the tires hold together when you do this is actually kind of remarkable. The surfaces are going amazing accelerations. Okay, but the point of this is that you don't actually want to skid the tire for two reasons. I mean, one of them is it doesn't give you quite as good a grip. The other reason is that sliding process is destructive of the tire. They talk about burning rubber because you can burn rubber. Where does the temperature, the thermal thing come from in order to do the burning? Well, it comes from a feature. Is it a feature or a bug? A feature of sliding friction that has to do with this question. So I'll ask you one more question, and I think I'll be done with questions. If I take this box and get it started, and then, so the story was during the stopping process. We got two objects, the table and the wagon, or a box on a wagon. Who's doing work on whom? So the question is that. Here's the question. Okay, this time I got 5 choices. So people, if you got an F on your clicker, you can do it, but I don't think you got one. All right, so the box skids to a stop on a motionless table. What work is being done by those two objects, table and box? Any questions about the question? See what you think. I'll give you a full 60 seconds on this one, and you guys talk about it if you're at all unsure. And I will remind you to consider work, just focus in on, is object A exerting a force on object B? And is object B moving in distance direction of the force? That's all that matters. Don't assume conservation of energy or anything like that. All right, well, let's finish up. 5, 4, 3, 2, 1. The majority is not correct in this case. All right, so I will, it's sure tempting. That E was very tempting. The actual answer is A. So here's the deal. And this hopefully will help you remember the rules regarding work. Can the box do any work on the immovable table? No. If something won't move, you can't do work on it. Now, okay, if the purists, the super careful people go like, well, the table might move a little bit. Okay. In these questions, we assume the teeniest little bit doesn't count. You can't do work on something that doesn't move. So I can go pound my head against the wall all day and not do any work on the wall. It won't move, okay? However, the table can do work or negative work on the box because the box can move. And specifically, what does it do? Well, the box, in this case, was heading to the right, but the table pushed it with friction to the left. So the table was exerting a leftward force on the box as the box moved rightward. That's negative work. So the table did negative work on the box, sucked the energy out of the box. And you could see that because the box came to a stop. It lost its kinetic energy. It started with kinetic energy that I gave it by doing work on it, and then the kinetic energy vanished. Are you okay with that observation, that A was actually the correct answer, is the correct answer? So the table does negative work on the box and reduces there, while the wagon actually does work on the tiny element. Okay, so the question's coming in about where did the energy go, basically. Is this the same as when the car presses on the brakes? Yes. Yeah, but normally you don't skid the wheels, so the sliding effect is occurring not at the wheels, but at the brakes. But they are sliding against each other. So one of the questions coming in is noticing that that energy is really a conserved quantity. So where did the energy go? And it did get chopped up, and it got chopped up and converted into a relatively useless kind of energy that I just call generically thermal energy. It didn't vanish. What the box did was it did little microscopic bits of work on the table's top surface, sort of hitting the bristles and jiggling them. And so there was no overall work done on the table because the table can't move. But there were microscopic doses of work being done on parts of the bottom of the box and the top of the table. And those little microscopic biddies of work are now sprinkled randomly in those surfaces, making them hotter. So you can detect that hidden energy in the temperature of the surfaces. They've gotten hotter. So that brings up the idea of thermal energy. In short, sliding friction produces thermal energy. It basically takes useful work and turns it into relatively useless thermal energy. And that addresses these questions. What does positive and negative mean? Positive work means that you're giving something energy. For example, the table, if I push the box to the right, I will do positive work on it. There. I pushed it to the right as it moved to the right. The table pushed it to the left as it moved to the right. It did negative work on it, sucked the energy out of it. So I put the energy in. You could see it in the form of the motion of the box. It's kinetic energy. And friction sucked the energy out, did negative work on it, and you could see it in the loss of kinetic energy. Where'd the energy go? It's thermal energy. All right? So what's thermal energy? So the last thing to do here is to talk a little more about energy. Energy comes in a variety of forms. I'll remind you, energy has no direction. It's not about movement, it's about the ability to do things. Moving objects have energy, specifically kinetic energy, but which direction they're heading is irrelevant. I've got kinetic energy, I have the same kinetic energy. Energy didn't care that I was going to the right or left. Kinetic energy is the energy of movement. The other normal form of energy that's around is energy stored in forces, what's called potential energy, broadly potential energy, but there are many specific potential energies. So gravitational we've seen already. That's the energy that's stored in the forces between the object and the Earth. Instead, we assign all of that stored energy, even though it's between the Earth and say a ball or a weight, because I don't have a ball. We assign it all to the weight. Why? Because you can't get the Earth to move very much. So you can't sort of do work on it, put energy in, take it out. This is going to do all the moving. And so saying that this guy owns the gravitational potential energy just makes sense because that's what's going to move and give away the energy or receive it. You're not going to be able to do much with the other end of that bargain, the Earth. It's going to pretty much just sit there. So gravitational potential energy. Other kinds of potential energy. You ever have one of these? No. Uncle Otis, do you want some mixed nuts? Mixed nuts. Ah, it's a snake, okay? Right. There's a spring in here, right? There's a spring that's stored energy in the forces between its parts. And I'm going to do work to put it back in, as I did when I was, 5? And then you would naturally go to the same person. Uncle Otis again. I don't have an Uncle Otis. You want some mixed nuts? And once again, amazingly, Uncle Otis was surprised. Okay, so you can call that elastic potential energies. It's stored in the elastic character of various objects. Other energies. Magnets. Two magnets arranged so they attract each other, and you live in an era when really powerful, very inexpensive magnets are available. It's great. Watch the table actually has lots of metal in it, steel in it, the grass. But these guys, they've got stored energy too. And as I get them closer and closer together, they can do work on each other and pull together. That released energy. So they were storing, you can call it a magnetic potential energy. Chemical potential energy, or electrochemical. a bunch of batteries. There's energy put into them at the factory. It's in chemical form, but it is capable of doing work. And actually, it can do work by moving electric charges around. And what I'm going to do is show you electrostatic potential energy. The energy stored in the forces between electric charges, which we won't be doing to any extent this semester, but you know that opposites attract, the conventional argument. If you have positive charge, which is an interesting, what's charge and what's positive about it. If you have positive charge, we'll not worry about those. Positive charge here and negative charge there, they attract each other. And they can do work as they pull toward each other. If you grab them and fight the attraction, they will do work on you. They'll pull your hands together as your hands move together. They do work on you. So I am going to pull them apart right now. I can't do it with my fingers, but I can do it with the help of the batteries. And I will. So the batteries now are pulling apart positive charge and negative charge. Positive charge and negative. They're accumulating big doses of positive charge on one end and negative charge on the other. And it actually takes a few seconds for this to happen. There's a lot of work being done. And the energy now is stored as electrostatic potential energy in this device. This is a charge storage device known as a capacitor. It looks like one object, but it actually has a surface on which you put positive charge and a surface on which you put negative charge. And if you let them get back together again, they are super happy. Okay? Ready? Get set. You want me to do it again? Yeah. Oh, nobody ever says no. You didn't like blowing stuff up as a kid? Yeah. I only got picked up by the police once. It was very traumatic. I was much younger than you guys. All right. So I'm going to let them get back together again. Ready? Okay. After class, you can try this again. All right. Let me finish with one thing. All of these are orderly types of energy. That is, they're equivalent to work. They can do work easily. When you chop the energy up into little pieces and make thermal energy, you can't do work with it anymore, or not directly. It's very hard. And I will talk next time about why thermal energy is so hard to do anything with. All right, thanks.